Alright, hello everyone. My name is Pavel, but I go by Pasha, and a year ago I graduated from NC State University with PhD in Industrial Engineering, and Benil Starley is my advisor. It's been a year since I started working at Dow Chemical Company, which is very weird because I do robotics, being in PhD in Industrial Engineering for a company that does chemical engineering. This is not related to what I do at Dow Chemical. Last piece of my dissertation was about industrial metaverse and how those digital twins can supplement small and medium enterprises. And one of the problems that we have encountered is that it is hard to get into digital twins. So we know that digital twins are virtual replicas of real hardware, and it is connected by data. It is used for monitoring, prediction, and simulation or motion planning, and it is essential for industrial metaverse, which is bigger picture that includes digital twins. And we've seen that big companies like Siemens, BMW, Bayer, and Amazon Robotics, they have succeeded in this case. They proved that digital twins work, and they can give you substantial reduction in spending or time being spent for designing things. But there is a gap for small and medium enterprises. They have limited resources, it is complex, there's lacks of experience of making digital twins. So in this table, there are just several aspects that compare different parameters for SMEs and large enterprises, where we see that they have different nature, and for small and medium enterprises, they are focused on something easy to implement, out-of-the-box solutions. Their scale on actually getting real profits right now from digital twins. Where large enterprises, they have more budget, they have dedicated teams, they have resources to build custom-made solutions for digital twins. And still, SMEs account for about 90% of manufacturers in the United States by quantity, but also they are subcontractors for large companies. And yet they cannot afford enterprise level digital twins. So there's a need for a new approach, and there is a gap between potential and reality. So just to highlight again that SMEs especially impacted due to limited internal development teams, high cost and complexity of traditional, even though digital twin is not that old, and there is challenges in integrating legacy equipment. So research goal and contribution of our work was to demonstrate a practical
low cost for low code, no code, and with open resources, open specifications framework that uses Node-RED, ROS2, and i16 for interoperability. As again, open standards, and in our work we use one-way monitoring for CNC machining and two-way for control of robotics. And talking about low-code and no-code platforms, I think most of us are familiar of some of those products. Those are computer-aided manufacturing. And those are the tools that are being used to generate toolpath for CNC machines and convert it to G-code. So this is probably one of the technologies that small and medium enterprises have already tackled. So this is, I doubt there is any company using manual G-code creation in order to make complex parts. So this is already in the pocket of SMEs. The next one is robotics. Collaborative robots, they implemented this low code or no code. You see universal robots, Polyscope, FANUC-TP pendant teaching, or ABB, easy programming, where you just drag and drop different nodes and it allows you to control robotics. One of the pieces of software is called Blockly, is being used for creation of software, just drag and dropping pieces together. So we see that robotics also can be implemented using low code and no code solutions, and they still can be learned by SMEs without anyone being a real roboticist. And the third part is when we're talking about integration of some higher scale automation, there is a tool which is called Node-RED. It is It comes pre-installed at Raspberry Pis, which is a Debian kernel of a Linux system, which is also Ubuntu. So you can install those there. Revolution Pi, those are industrial-grade Raspberry Pis, up to 22, or Phoenix Contec, Wago. They have PLCs that run Linux, and you can use Node-RED there. Siemens, some of the Siemens PLCs that run Linux and Rexroth, they can run Node-RED there, so you don't have to use ladder logic diagrams or functional block diagrams, even though Node-RED looks like function blocks. And in this screenshot, you can see those are pieces of Node-RED program that are used to get data from Haas CNC machine and publish it to a broker via MQTT to some topic space. You can also build dashboards with Node-RED. So this is a dashboard built in Node-RED. So this shows that without any actual software expertise, you can build software that can get data, and then it can visualize it in some way, not being a computer scientist. So in creation of digital twin framework, there is already existing ISO standard, which defines different levels of digital twins. And we decided to follow this one, where in our OME level, those are physical assets. We have VF-2 CNC machine, and we have UR10E collaborative robot. For device communication entity, or how we talk to those machines, we use MQTT protocol with Sparkplug specification for VF-2 CNC machine, and ROS2 for robots. For digital twin, we chose a NVIDIA Omniverse, and specifically NVIDIA ISAC app that will be used for visualization of digital twins and also motion generation for robots. And for user entity domain, we are using Node-RED as dashboard for CNC machines, or as well Omniverse for visualizing what the robot is doing specifically, which also can be used to generate commands for the robot. So again, this is a one-way or digital shadow for CNC machine, which means that we can observe what that machine does, but we cannot send commands. Why? Because in one of the first presentation today, when you have industry-grade professional CNC machine, it is not made for research. Even though we were able to send some commands in order to run separate lines of G-code, it's not recommended because it's going to be a horrible machine part. But for UR10E collaborative robot, you can create trajectory path and then send it to a robot to create both-way communication for digital twin and physical asset. So those two cases illustrate the spectrum that you can monitor and you can control assets with digital twins. And just for those cases, for OME, our CNC machine generates XYZ positions, spindle status, and tool data that is pulled by Telnet protocol via Node-RED and transmits that data to digital twin via MQTT SPB. And then our Omniverse receives and visualizes that data and provides passive representation or digital shadow of that machine. And Node-RED dashboard displays real-time telemetry using that Node-RED. So there's no control over that physical asset. For Cobot, those are joint commands that are being published, and we're using ROS with RTD and DDS to allow for both-way communication with digital twin and physical asset. And Omniverse is used to visualize what's going on with the robot, as well it allows for collision checking and motion generation. And then for user domain, ISAC sim can be used to visualize, as well as you can create a custom graphic user interface to control the robot. For Haas, we used event-based update, so it means that MQTT empowers and actually tries to use report by exception principle, which means that publish data only when there is a change. So let's say machine is standing doing nothing, or maybe spindle is rotating at the same speed. There is no need to publish the data because it doesn't change. That's why Node-RED does pull the data from CNC machine in like 10 hertz frequency, but it doesn't publish it to digital twin at that frequency, only when it changes. And for UR10E, because it's ROS-based, there is already sampling rate for ROS, and that's why it's time-based, and it implements ROS bridge for talking to digital twin. In the workflow, how to make those digital twins, we just download STEP or IGES files, open them in Fusion, convert them to USD, which is a universal scene description. It's a format that is used by Omniverse to create objects and scenes and worlds and everything. And for VF2, we did that. We just downloaded official models, rigged them, created joins, so-called X-forms. And for UR10E, you also need to create URDFs, or Universal Robot Description files, in order to have kinematics on that robot, in order to control it. RMP flow, that's a Romanian motion policy. This is a framework that's used for dynamic obstacle avoidance, so you don't have to tell how to avoid. You just tell it where to go from and to, and then using any obstacles in that digital physical space, it creates the motion and a trajectory for robots to go there. And it's cool that it is dynamic. So it means that if you have some rigid body that is on the way of the trajectory and it's moving, your robot will recalculate that path on the fly to avoid it. So in this video, we just show, here we can see CNC machine. That's a sub-second delay where we are moving this robot just manually. I'm just manually moving in just jogging mode. You can see I'm just getting XYZ positions, and our digital twin responds correspondingly. The good thing is, you see I have doors here, the physical asset. In digital, you can remove those doors, so you can bypass all those safety systems just to dive inside and see what's going on, because maybe you have some obstacles or you have some blurry doors, you can't see anything. And you can open doors in the digital twin. You cannot do that in the physical machine unless you bypass safety. For robots, in this first video, we show digital shadowing. Like I'm using pendants, so I'm pressing just tablet and move the robot, and you see the Omniverse robot is also moving and showing exactly the same thing in real time. When I'm saying real time, that's like 10 hertz falling, so it's pretty quick. And you see, I can even just manually drive it up and down, and it's following the same thing in Omniverse. And it is obvious because it basically just copies the joint position of the actual robot. And for the opposite control, we see that in Omniverse, I'm just dragging that triad in Omniverse just manually. And when it succeeds at generating that path, then it publishes it to a robot so it can do exactly the same thing that I was doing in Omniverse. Which, if you think you can add some computer vision base or any other logic into your software for Omniverse, and whatever it's going to do in virtual space is going to do in physical space too. Or if it encounters something, that's also going to be mirrored to a digital twin. So this gives a path to machine-to-machine communication, where we have different pieces of hardware that we would like them to be talking to each other. And there are different cases we can use it. For predictive maintenance, so machines like Haas, they can just publish some parameters, and other supervisory systems can issue alerts or anomalies. Or, when needed, we can use the data collected while something happened, and then we can replay it in Omniverse to see what exactly happened. What was the position of tooling and everything when this crash happened, or something like that. For automatic quality control, so computer vision installed on robots can detect and make actions without actually stopping and calling operators. Or real-time data flow, when I showed you that we can get inside the work cell that is actually guarded for humans not getting in there, and see what's actually going on in there in this specific moment. And for inventory management and autonomous operations, so CNC machines can just talk to robots and order tooling when we have to, like, we replace those tools or parts or anything else. So they can talk to each other through MQTT and enable this autonomous operation. That is done not by coding, but by drag and dropping those functional blocks. This is a piece from Omniverse. Those are called action graphs. So in the ground level, it is a code, but it's already built in a graphical way where you just connect those nodes to each other, and that's it. And it works. You don't have to write any custom-made piece of software. So for human-to-machine interfaces, we still need humans for error detection, and unexpected task and safety when humans have to talk to machines without being coders or something like that. So those are technologies that enable it, is like no-code and low-code platforms, industrial metaverse with AR, VR, where we can see stuff, and computer vision, which allows machines to see things as we see them. And the communication loop is that machine sends state and sensor data to digital twin, then human responds through dashboards or manual controls, and then robot takes those inputs and adjusts its own actions based on human interaction. So the enabling technologies are on this slide. Most of them are very, very affordable. Some of them are free. So Omniverse is free, Node-RED is free, Unity, Gazebo, those are free. Onshape is free CAD tool. And those are tools that small and medium manufacturers can use in order to create their own digital twins. You don't have to have custom-made software piece for you. You can just use the set of those tools to create digital twins. And the benefits of our framework, it simplifies digital twin integration using open protocols or free tools like Omniverse. It reduces complexity, and it provides a path for digital twin because there is an ISO standard that tells you how to build a digital twin in architecture. For your teams, you don't have to have computer scientists. You can just use low-code, no-code platforms, non-expert users creating digital twins, and this gives you more opportunity to build it. As well as digital twins, they allow quick reconfiguration and real flexible manufacturing cells, and also facilitates some remote operations where you can do a nights out operation and you can see what's going on just sitting in your office. And the technologies that will help there are already there, are Raspberry Pis or Jetson Nanos. Those are edge computing devices that are capable of running a lot of things. Some tools like GPT-4o or Project Root by NVIDIA, they support autonomous decisions, so you can use those APIs to create autonomous systems. And some wireless connectivity technologies allow low latency for digital twin and physical assets together. But there is still limitations and challenges like everywhere. So one of those is scalability. So with those low-code, no-code solutions, they are usually for a small amount of equipment and data. And scaling up may pose limitations on this framework. Customization and flexibility, so of course it's out of the box, drag and drop, but then there can be some edge cases where it's not going to work and you still have to write some piece of software. And security and latency. Small and medium enterprises don't have usually dedicated cybersecurity teams or IT departments that can maintain this MQTT and ROS2 network issues that can come up when you are working with your digital twin. And the directions in the Metaverse for small and medium enterprises include AI integration. So with this, OpenAI and other companies developing models and making them accessible. So there is a path for small and medium enterprises to take those tools and use them in their digital twin implementations. Cybersecurity. So there is a call for like secure communication protocols, because MQTT in itself is not very sophisticated in this way, and scalability. So we also looking forward for developing frameworks that can be cloud-based or service or software as a service, where you don't have to actually have your actual IT hardware, so you can just use some cloud services. So that's all of my presentation, and I'm glad to answer any of your questions. Thank you. Yes, please. Yeah, so you saw this piece of videos. That was the last piece of my dissertation. I didn't have time to get to work. And I was like, okay, we can do rigid bodies, right? But how can we do flexible bodies, liquids, and everything? And Omniverse allows for it. I'm following one guy on LinkedIn that's showing that you can cut cucumber and banana inside Omniverse. So you can do deformable objects in Omniverse. So that's an interesting topic. So Omniverse does include capabilities for building like digital replicas of what you're going to do. So, and in today's work, the very first presentation, they were talking about chip generation, right? So if you can include modeling of chip creation while in the process, this can be a really good opportunity to even bring this gap like closer in connecting digital twins and physical assets together. But yeah, I'm looking into working in this digital twin to create some liquid-based things and soft materials too. Yeah, thank you. Yes, please.
So follow up on his question. If Omniverse has the ability to predict the effort or the expected, amount of activity in order to turn the spindle, to move the arm through space, it would be very interesting to be able to capture exceptions. Like this machine is working harder than I expected to.
Yeah.
Or I'm working easier than I expected to. Maybe the work piece is missing. Things like that in order to capture exceptions would be useful. So you say the Omniverse, when someone's cutting a banana, can they feel the banana? Can they tell
yeah.
how ripe that banana is?
I would say it is possible. You don't see it in the background as we don't see it in real life, right? When we cut it, right?
That's cool, but
yes, but it's not only picture because that while you're cutting, you can see that it actually starts moving because there is forces acting against it. And Omniverse allows you to do a lot of stuff. So, and you can build your own extensions. It means that I assume there are the companies that build those physics additions to it. They do it because when we were working 2 years ago in our article Unreal Factories, we were using Unreal Engine. And we encountered the problem that okay, we're cutting through metal, but we don't cut chips actually. But it would be nice to do so. And I see that current technologies already, the simulations allow you to do that. So it will be nice, as you're saying, like not only do the visual part, but also having the physics and forces and everything. And I know that you can get that data out of Omniverse.
machines can be poured out.
Yes, you can do it from both ways. You can do it from machines, the real data, and you can port it from digital twin, and then you can try to see, okay, why they're not matching. Maybe there is some inconsistency over there. Yeah.
Okay, because of the time, let's finish today's presentation. Please give a big
All right.
round.
Thank you.